Bismillahirrahmanirrahim. Now we come to the second operating condition, that is when we have fixed input voltage but variable RL. In the second operating condition, we have a fixed input voltage and a variable RL. Now, due to the offset voltage Vz, there are specific range of resistance values that will ensure that Zener is in the on state. Too small a load resistance will result in a voltage VL across the load resistance less than Vz, and the Zener diode will be in the off state. So we have to be very careful while designing the load resistance, because if we design a load resistance that is too much small, then this small RL will cause the voltage across RL to be less than the Zener diode breakdown voltage, and the Zener device will be turned off. Now, to determine the minimum load resistance of figure 2.112, we will turn the Zener diode on, simply calculate RL, that will result in a load voltage VL is equal to Vz. That is, we will find RL such that the voltage across RL is equal to Vz. So we have Vz is equal to VL is equal to RL multiplied by VI divided by RL plus R. And from this equation, we can manipulate and find the minimum value of RL to be equal to R into Vz divided by bracket VI minus Vz bracket closed. This is our minimum load resistance. And any load resistance value greater than RL obtained from equation 2.20 will ensure that Zener diode is in the on state, and the diode can be replaced by its Vz source equivalent. The condition defined in equation 2.20 establishes the minimum RL, but in turn specifies the maximum IL. When we have minimum RL, it means that we are providing the maximum current, and our maximum load current is given in equation 2.21. IL maximum is equal to Vz divided by RL minimum. And once the diode is in the on state, the voltage across R remain fixed at VR is equal to VI minus Vz. Remember that in this condition, we are taking input voltage to be constant. Therefore, VI is constant and Vz is also constant, and VR will also be constant. And IR, that is the current flowing through R, is fixed at VR divided by R. Equation 2.23. And our Zener current is given in equation 2.24. It is equal to Iz is equal to IR minus IL, resulting in a minimum Iz when IL is a maximum and a maximum Iz when IL is a minimum, since IR is constant. Now Iz will be minimum when IL is maximum, and Iz will be maximum when IL is minimum, because we have a variable RL. Therefore, the minimum load current is given in equation 2.25, whereas the maximum load resistance is given in equation 2.26. So now we will come to example number 2.27. The statement of the example is, part number A is, for the network of figure 2.119, determine range RL and IL that will result in VRL being maintained at 10 volts. So we have to find the range of RL, the maximum and minimum range of RL, and the maximum and minimum range of IL that will result in VRL to be maintained at 10 volts. And the second part is, determine the maximum wattage rating of the diode. So in this example, let us look at the circuit diagram. We have an input voltage of 50 volt. Then we have a series resistance R of 1 kilo ohms. And then we have a Zener diode of 10 volts. And the maximum current that this Zener diode can handle, or the maximum current that can pass through the Zener diode, is 32 milliampere. And we have to find the range of RL. We have to find the maximum and minimum range of RL. Our input voltage is 50 volt, R is equal to 1 kilo ohms. Zener diode voltage is 10 volts. and maximum current that can pass through the Zener diode is 32 milliampere. We have to find the range of RL. So the solution to part number A is to determine the value of RL that will turn the Zener diode on. Apply equation 2.20. We will assume that the voltage across the load or the voltage across Zener diode is equal to 10 volt. That is, the Zener diode is turned on. Thus, the minimum load resistance is equal to R into Vz divided by Vi minus Vz. That is equal to 250 ohms. Now, RL minimum is 250 ohm. Now the voltage across the series resistance R is determined by VR is equal to input voltage minus voltage across Zener diode, that is 50 volt minus 10 volt equal to 40 volts. And equation 2.23 provides the current flowing through resistance R, that is IR is equal to VR divided by R, that is 40 volt divided by 1 kilo ohm, that is equal to 40 milliampere. So we have a input current of 40 milliampere. Now the minimum level of IL is determined by equation IL minimum is equal to IR minus IZM. This current IR will not change. It is constant. It is constant. It is equal to 40 milliampere. But the Zener current can change from minimum current to maximum current, and our maximum current is 32 milliampere as provided in the statement itself. So the minimum load current will be 40 milliampere minus 32 milliampere is equal to 8 milliampere flowing through IL. Remember that this 40 milliampere is the constant current that the circuit can provide. This 40 milliampere is the constant current that the power supply will provide under such circumstances. And our load current will be extracted from this 40 milliampere alone. And the minimum load current is 8 milliampere. This 8 milliampere is the least load current. The least load current will be provided by the maximum load resistance. Therefore, RL maximum is equal to 10 volt divided by 8 milliampere is equal to 1.25 kilo ohm, and 250 ohm is our minimum load resistance we can apply. And for the part number B, we have to find the power dissipated. The power dissipated is 10 volt multiplied by 32 milliampere. It is equal to 320 milliwatts. This is the maximum current dissipation of the Zener diode.
Excuse me, sir.
Yes.
Sir, let's analyze our circuit with the load resistance of 200 ohm or less than any value 250 ohm.
Okay. Sure. So the question is, what will happen to this circuit when we use RL less than 250 ohms, correct?
Yes, sir.
So now what will happen? To answer this question, let us assume that our RL is equal to only 200 ohms. Okay. We have an input voltage of 50 volts, R of 1 kilo ohms, and RL of 200 ohms. Now let us analyze. How should we analyze? In the first step, let us remove the Zener diode. Let us assume it is not connected. With this assumption, what will be the voltage across RL? What will be the voltage across RL with the Zener diode
Sir,
being removed?
10 volt.
It will be equal to, no, it will, we cannot assume 10 volt. We have removed the Zener diode. We will have to calculate, we will now have to calculate the voltage across RL by applying Kirchhoff's voltage law. And that is equal to the current under such circumstances is the load current under such circumstances is input voltage Vi divided by R plus RL. It is equal to 50 volts divided by 100 1200 ohm. So IL is equal to 50 volt divided by 1200 ohms. This current is equal to 0.04 ampere. Now let us multiply this 0.04 ampere with 200 ohms of our RL. We get V voltage of the load, that is equal to 0.04 ampere multiplied by 200, which is equal to 8.3 volts. Now, when we use a resistance of 200 ohms, or when we use a resistance of value less than RL minimum, then voltage appearing across RL will be less than the Zener diode. As shown in this example, we get 8.3 volt, and this 8.3 volt is not enough to break down the Zener diode. Thus, 8.3 volt is not enough to break down Zener diode. The Zener diode will remain open circuit. It will not be operating. So we have to take care while deciding RL so that we use a value greater than the RL minimum.
Sir, if we apply a normal diode instead of a Zener diode in reverse bias and with the reverse voltage of 10 volt, will it be same as a Zener diode?
Zener diodes are our normal diode with the slight modification that the breakdown has now purposely been lowered. The normal diode breakdown voltages are kept very high, whereas the breakdown voltage of Zener diode is kept controlled, it is kept variable. That is the only difference between the normal diode and the Zener diode. The rest of the operation remains the same.
सर पावर डेसिपेशन किसके अक्रॉस ज्यादा होती है, नॉर्मल डायोड या जीनो डायोड के अक्रॉस?
नहीं देखिए, power dissipation is the product of voltage across the diode multiplied by current through the diode. If we are working within the limits as provided by the manufacturer, then both diodes, Zener diode or the normal diode, can handle the current. But if we purposely make current larger, more than the current the manufacturer has specified, then we will break down or we will rupture any diode, be it normal diode or Zener diode or any special diode. Okay, so thank you very much, class. Please go through the examples, read the theory. Reading from the textbook is highly recommended, and solve the example that we have done today. Run them in the simulation software also and confirm the results. Okay? Thank you very much. Assalamu alaikum.